All right, hi everyone. Welcome to our special Friday seminar. Today I'm very happy to introduce Raul Jimenez, who's visiting us just for one day. Stop over in Sydney while he's on a very nice sounding holiday.
Yes, that's right.
So Raul is a expert on cosmology. He works on a very wide range of things, and I assume today we'll be hearing about a very wide range of things related to cosmology. So thank you for taking the time out to give us the seminar, and I'll leave it in your hands.
Thank you very much. Thanks for hosting me and organizing everything. By the way, it has been really nice. I'm a long old friend of Celine, right? And it was nice to stop by and see her. And actually, it's very nice to be here for the first time at the physics building. So, of course, this is going to be very informal. So feel free to interrupt, complain, throw tomatoes, whatever you like to do. But the more interactive we make it, the better. I think it will be more interesting. What I want to talk about for the next 45 minutes or so is about the effort we have been doing in Barcelona to try to understand the universe. I know it sounds very arrogant, but at the end of the day, it's what we do, right? We try to understand the universe, right? So our approach has been what we call model-independent cosmology, and I'm going to explain a bit why that approach, what we are doing, what we have learned so far, and how we think we can move forward in the future. So the situation is as follows.
Yeah, it's fine.
Yeah. The situation is as follows. We do have standard cosmological models, called the numbers in the end models, but with 7 numbers, these 7 parameters that you see here, the energy densities, the current expansion rate, the amount of free electrons in the universe, plus some characterization of the early inflationary state, the amplitude and the scale dependence, give you basically the full observable universe. So bear with me a second. I can put these numbers in a computer and I can produce basically everything, with some exceptions that I'm going to talk about. But as nice as it is, the description is not the same as understanding, right? We don't know what the dark energy is. We don't know what the dark matter is. We also don't know why there are atoms and not photons, because there should be only photons in our equations. The matter-antimatter asymmetry, maybe there are models for that, but it is certainly not proven. And by no means we know what the inflaton is. So there is something else that we need to do, actually progress on this front, right? So it has been a phenomenal understanding. If I was giving this talk 30 years ago, we would be discussing about warm dark matter, cold dark matter, mixed dark matter, maybe not dark matter, maybe something else, like topological defects to make the structure, inflationary models, open inflation. Everything was very open in the air. So, as I said, it can almost describe the whole universe, but then there are cracks that are appearing, right? And that's how we play the game. We just look at the universe, try to see what the model fits, and then we try to figure out what the model doesn't fit. So the 3 cracks that I think there's only one significantly statistical, relevant, and robust crack, which is the one about the expansion history of the universe, the Hubble tension, and I'm not going to dwell on that. You know very well what it is. The early universe is a screen, is the CMB. You assume a model, you project all the way down to the redshift 0. It gives you a number. When you do the direct measurement, it gives you a different number, about 5 sigma discrepancies. There are some hints, or I don't know how to call it, maybe indications. One is the amount of structure we have at the scales of about 8 megaparsecs. The same game, the CMB is giving you a number. The local weak lensing surveys give you a different one, only 2 sigma discrepancy, probably not worth writing home, but you know, we are desperate to try to understand what the dark matter, dark energy are, so we look at everything. And now, of course, with the DESI survey, there is this claim that maybe the dark energy itself is evolving, right? This is still very, very preliminary, but I get attacked if there is somebody from the DC collaboration in the audience that I didn't mention this. So I mentioned, to my best of my knowledge, what are the things. Now, this is a particle physics sort of mixed audience. So let me remind you, in cosmology, you can only be Bayesian. There's no way you can be a frequent. This is impossible. We don't do experiments. We only do observations. And the sky is out there for us to observe. That's all we can do, just collect data. And bear this in mind because it is important when we are doing inferences. Now, as I always said, that observational cosmology should be almost a finished business because we already have examples of ultimate experiments. This is the temperature, primordial temperature of the CMB, of the cosmological background, as taken by the Planck satellite. There's no need ever again in the history of mankind to take this data because that's it. They are cosmic variance limited. The data cannot improve, it's impossible. So you can collect all the data, put it in a web server, and let the smart students figure out what is going on. It's a very different game than doing experiments in particle physics, right? When you design the experiment, you do it as many times as you need, you change the experiment, right? When you don't get more than 1 sigma, right? You change the experiment, then you get 20 sigma, right? Well, here we cannot play that game. It's impossible. So we have to be very smart at dealing with the 1 sigmas or the 2 sigmas and trying to understand what it is. Now, it's not only the CMB. Look at this progress in collecting galaxies, right? So this is what we call the large scale structure, where we just look at positions and redshifts of galaxies, right? This is really very much the work of a cartographer, right? Angles and redshifts, not even distances, we just collect the redshift, right? But if you look at the fact that it is 1983, and this is 30 years after, how much we have evolved in logarithmic scale, right? It's really remarkable. This is DESI, first year data were just released, and you know, we keep pumping up there. The prediction of that line is by 2060, we should have collected all the galaxies that are confusion limited. That's it. You know, you keep observing many, many galaxies. At the end of the day, you fill up the camera with the size of the galaxies. So, as I always say, observational cosmology should have been finished already. It's not a question of technology, it's actually a question of money. We do have the instrumentation means to actually do observe the whole sky. And we should have done it. This is a question that we have, of course, very little. So, I'm telling you about explaining things, but at what point do we stop explaining things? Let me tell you something. Nobody on his own mind, besides all these emails we get from retired engineers, is trying to get a fundamental theory for why there are total eclipses of the sun. I mean, why the angular size of the moon and the sun are exactly the same. Just happen to be there. Also, why do we have as much water as land coverage on Earth? Why is the contrast so tiny between the bottom of the sea and the top of the land, right? About a few kilometers, over almost 10,000. These are coincidences, right? And again, if I was given this talk before 1995, when we didn't know about exoplanets, we will say, well, it's very strange, right? That we're so fine-tuned. But now we know there are basically exoplanets everywhere, in every single star of the galaxy. So we are just sampling from the distribution. We're just lucky. We are very lucky in the solar system. The moon is at the right position. We are far away from the center of the galaxy, so the explosions don't bother us. The gamma rays don't destroy our ozone layer. Many, many of these that I can talk, right? So let me give you like a little quiz. I wake up in the morning. I'm married to an Italian woman, so I have to make coffee, right? It comes with the contract, you know, with the regulations. So imagine I wake up and I see one single coffee bean at the edge of the countertop. My question for you is, where is the rest of the bag? where are the rest of the beams if I only see one there?
On the floor.
Exactly, on the floor, exactly. So the most Occam razor thing that I can say is that these beams have fallen and got all the way to the floor, and then just, by chance I see one there. Right? The other explanation is that my daughter woke up in the middle of the night and put it there by hand. But then that's fine-tuning, right? So at what point do I stop explaining the universe? I think it's a very interesting question. For most of these things, they have no answers. What I'm going to present here is a very modest attempt to explain things, right? So as I said, we are Bayesians, right? We have to pose a model, deal with the prior, and then make an inference for the posterior. We better calculate our likelihoods. Now, being Bayesian is very nice because then you have a robust framework. You have a likelihood that you can compute, you have a prior, you deal with them, and then you infer the parameters of the model. But there's a more interesting step, which is the following, is which model is the best? But Bayesian inference tells you what you have to do. You compute the evidence. The evidence is just the integral of the likelihood times the prior. And there are two complications with this approach. One is that then the evidence is always going to depend on the prior. When you do parameter estimation, the data eventually overcome the prior, right? More data, but here you're stuck. You cannot get rid of it. And the other horror, and this is the technical one, is this is a multidimensional integral. And if you have many parameters, it will take you forever to do these integrals. So people don't do evidence because it is too complicated. But I'm going to show you a case where you can actually do evidence, and it is related to neutrino cosmology. But before that, let me give you an example of what I'm trying to say about evidence. This is important because we want to choose our model, right? We want to decide which model is the best. For example, if I put a model with lambda CDM and I put a model with no dark matter, which one is the best? How do I choose? So this is a very simple example, right? Imagine that I have data, which is just this vertical line, right? And I ask, which prior should I choose? The red, the green, or the blue? I tell you, I posed this question to my little twin daughters. They are now 12. They told me the red one. And I said, why? Say, looks good. Actually, it's the right answer. There is no objective. Actually, it's the right answer, right? There is no objective criterion to actually define what the prior is, right? So you can say, okay, M1 is too simple because it is a delta function picked somewhere. M3 is too complex because it can generate anything that I like. M2 is just right. Very good. But that thing was basically based on my prior choice. And, there are many ways to choose the prior. And what I'm going to present right now in the next few slides is a way to deal with the prior based on the physics knowledge. So let me talk a bit about neutrino cosmology. So neutrino cosmology is exciting because it's probably the fastest way to get a detection of the fact that neutrinos must be massive. So we know from the oscillation experiments that there is a mass difference between the eigenstates, therefore there must be a mass somewhere, right? Now, how does it work in cosmology? Well, it is very easy. If you have a lot of neutrinos that are part of the dark matter, because these guys are hot, they tend to get out of the potential wells, and therefore they smooth out the power spectrum, right? So if you were computing the power spectrum, if you have something as heavy as an electron volt, you will have an effect of about 50% on the small scales in suppressing the power spectrum. So basically, what you try to do is to keep looking at this effect and see if you can detect that much. We are not there yet. We only have upper limits. And it's actually even worse than that because we do not do it that way, which is the proper way to do things. What we do is we put an extra parameter in the lambda CDM, and then we run our Markov chains with that extra parameter. So it is something called neutrino-like, but in reality, if you want to claim that you have detected a neutrino, you should see something like this shape. Okay? But given that caveat, we do have, okay, here I was emphasizing, if you do a full calculation, right, if you just really like to understand this and you put it in the Boltzmann code and try to figure out what it is, this is the way the power spectrum looks like. And there are several effects that I don't want to enter into because they are very technical. But basically, this is the signature you should see, but we are not there yet. We haven't seen that signature. So what we do, actually, compute from our surveys and our STMB data, an extra parameter that we call neutrino-like, and then we put constraints on that mass, right? So basically, nowadays, we are somewhere here, 0.09. For the sum of the neutrinos, we cannot distinguish yet among the different neutrinos. And remember that the oscillations are about 0.06, the delta mass of the oscillation. So we are really, really close. We are very, very close to actually get the detection. And I bet that in the next 2 years or 3 years, when DESI collects and Euclid collects more data, we are going to have neutrino detection. Now, a very interesting point is, how do I know it is a neutrino and not something else? And we have written about that. And this is something that we're going to get the rage of the particle physics community, because they are going to say, okay, how do you know it is a neutrino, right? How do you know? Well, they are going to be doing the Catherine experiments, and I will show you they are not going to get all the way down to where the neutrino mass is expected to be. So this tension is going to, we have to address as cosmologists this fact, right? When we claim that we have discovered the neutrinos. So I'm going to address a different question for which I have an answer, which is the following, okay? So I can plot here the total mass of neutrinos versus the lightest neutrino, right? And if I do that, I can live only in 2 places. One that is called the normal hierarchy, where I put the electron neutrino at the bottom and I put the 2 lightest ones at the top. This is how you organize the eigenstates. Or inverted, that you do the opposite, you put the electron neutrino as the heaviest one, or degenerate, where all the neutrinos have the same mass, right? So this is how you organize the eigenmass states, right? So if you do that on the total mass, you know, you can keep going down, and there are a few things to note. Is that eventually you are below 0.9 or 0.8, you are going to be excluding the inverted and the degenerate hierarchies, and you will be left with a normal one. The other thing is that ground-based experiments that look for a single beta decay are not going to be able to go that down, basically because they need gigantic amounts of material, right? And it's basically it's too much. You know, the cosmology will get there better. So where are we? We are somewhere here on this point. So this is from the latest, and latest I really mean a few weeks ago, data from DESI, large scale extraction, assuming that the correct model for the universe is the lambda CDM. And this is assuming that you have different models. For example, varying dark energy, arbitrary equation of a state for the dark energy. You basically liberate much more the thing, right? So then the constraint becomes a bit weak. But if you take this one seriously, you see that you are very low. Now, with the question that I pose, I'm going to pose and try to answer is, have we seen that the hierarchy of the neutrinos is normal and not inverted or degenerate? Now here is the Catherine whenever they finish the limit. So these single beta elements are way, way, way high up there. They are not tell us much. So we will have to relay on the cosmology. This is another way to look at the ground-based experiments in a different plane and see, you know, how things are looking at. But let me address the other question, which is a very interesting problem in Bayesian inference, and it is the kind of thing we are going to have to be doing. So So when you have a quantity that spans orders of magnitude, right? Orders of magnitude, you know that the prior you have to use, at least in one dimension, and this is demonstrated mathematically, is the Jeffreys prior, which is just in logarithmic beams, right? You just count in logarithmic beams. Right? This is the same thing that if you stop out there and see that bus number 35 arrives, right? The most likely number for the total number of bus lines in Sydney is somewhere between 1 and 100 or 1,000, right? Because if it was 40,000 bus lines, then you have been so lucky to see bus number 32, right? That it will be not very likely. So in the case of neutrino masses, we're spending many, many orders of magnitude because remember, the lightest neutrino of the three can be unbounded from below. So it can go really, really low, right? So you have 10 to the minus or 0.05 electron volts for the most massive neutrino. The second one could be at 10 to the minus 5, 10 to the minus 6, 10 to the minus 7, right? So you have a case where you're expanding. So which prior should I use? If I use a linear prior, then I'm going to be basically saying that my prior depends on the units that I use to measure the mass. It is much more reasonable to use a log prior. But then I can do something better than that here. I can say, okay, I'm dealing with a physics problem. So I know the physics. So let me use the physics as my driver. If all the neutrinos have or share a common origin for the mass mechanism, that's it how they get masses, right? Can be seesaw, can be whatever you like, right? Then they should have the same prior in the sense of exchangeability. It doesn't matter if I find an electron or a mu or a tau neutrino, right? So that will automatically set up the stage about how to choose the prior. So you set up the machinery, what you call these Bayesian hierarchical models. So you have a hyper prior that accounts for the masses, the mean, and the width of these things. You just use the oscillation and cosmological limits, marginalize over the hyperparameters, and compute the evidence. Now, this is a very beautiful problem because it has very few parameters. It has three. So I can actually do the calculation of the evidence because the integrals are not superdimensional. So let me tell you exactly what these things look like. So you do calculate the evidence, and what you have to look at is here. So this is the upper bound on the total sum of the neutrino masses. So 0.2, 0.1 here. This is the current limit given by the DESI data, and these are the odds that the normal hierarchy is preferred over the inverted hierarchy. And you can see already that with the current limit, there is a very strong preference about the order of a few hundred over 1 that the hierarchy is normal.
What is the meaning of odds?
Well, it is, so in these Bayesian comparisons, there is some scale that tells you more or less what are the chances that that model is preferred over the others. So these odds will be, what are the chances that the normal hierarchy is preferred over the inverted one? So it would be, they are like a few hundred, 300 over 1.
Is it like a ratio of the evidence?
It's the ratio of the evidences, yeah, that's what it is. So now, as the data are moving to a smaller and smaller things, and we are getting a bound, then it's becoming more and more evident that the hierarchy was inverted. But the right question is the following. Since you can choose any prior you like, you could also choose a prior that is a delta on the inverted hierarchy, and I will never overcome that. Your choice, you know, that you can say, no, I believe in that and I don't do anything. So the question here is, which prior do I choose? And our point was that you have to choose always the prior given by the physics, by your physics knowledge. If I was dealing with social sciences or human behavior, I wouldn't know how to guide my prior choice. So our claim is that the hierarchy should be normal. that it is already well established that the hierarchy is normal. In fact, when I give this talk in these gigantic particle physics conferences, they get very agitated, right? Because many of them have put a lot of money on experiments on the inverted hierarchy. But I'm happy to take odds of 300 to 1 that the hierarchy is normal. So, you know, we put $1, you know, if you win, I give you 300 back. But if I win, I give you $2. So it's up to you. Whoever wants to bet, I'm happy to take the bet.
Do you need to put in the neutrino oscillation experiments to have that?
You do.
Does the cosmology, does some neutrino mass constraint on its own not give you sufficient?
The cosmology is good. The cosmology is good, but the oscillations put you here, right? Yeah. So the oscillations make these two lines be very, very thin, right? Otherwise, I don't, right? So then I'm a bit, I'm going to be overlapping, right? So the oscillations are really, really good because they make these lines basically lines. And then I split these two cases very well. Okay, let's go forward. So that's the first exciting thing that I think is very interesting, that we are able to tell from the sky what the hierarchy is. The other, and you know, this is the latest paper we wrote about that in 2022. I think just we are waiting for the detection of the neutrino mass, I think 2 years. And then I want to write a very annoying paper called From Evidence to Evident. You know, because at that point, the signal, I just, look, I have been tenured for 30 years. I don't care about anything. I just want to see how many people get annoyed by that. But, well, it's not bad. Come on, like, you know, like being secure. But the other thing that we have done, and I'm going to mention it only, is the following, because this is another thing that you can do from the sky, which is completely counterintuitive, which is to distinguish if the neutrinos are Dirac or Majorana. That is, are the neutrinos their own particle, or do they have an extra family of antiparticles, right? Now, this sounds completely crazy because, of course, there should be no flavor sensitivity in this kind. But what you can exploit is the following fact, which is written in this little abstract, and I don't want to go into detail, because otherwise I will be talking only about that, which is the following. Gravity is going to change the helicity of the neutrino because it's going to deflect it, right? And the deflection is going to imprint in the helicity a change. So it's going to imprint a change of the helicity. And because you are having two different states, Dirac or Majorana, that are either their own antiparticle or not, then you're going to see that the cross-section of any future experiments of the cosmic neutrino background that detects it is going to change. It changes by about 20%. So if ever they get these Ptolemy detectors to work, and they can actually collect the neutrinos by looking at the cross-section about the flux of the neutrinos they get, they should be able to tell me if the neutrinos are Dirac or Majorana. Just basically because the deflection is going to change the helicity of the states. So we have done actually a few papers on this with simulations. We have a few of them coming out now with very detailed cosmological neutrino simulations that go to very small masses to actually pin down that effect. And now you can start to look into the Milky Way, and because of the structure that you have, you can actually see where most of the deflection is going to come up. So if instead of one of these Ptolemy, you get these tritium detectors, you get 4 of them, then you can triangulate the signal and figure out where you have to look to see this effect. This is something I just want to advertise, but I think it's going to be very exciting. People have done these experiments. I will finish here the part about the evidence of saying, okay, so I take all the data, and with some assumption on the priors, I can now look at several models. So for cosmological models, this is I'm talking about something else. I can put effective neutrinos, effective radiation. I can put extra curvature. I can put extra neutrinos. I can put, other things. And the conclusion from these evidence ratios is that the preferred model seems to still be the flat lambda CDM. So the vanilla model seems to be preferred according to this. So something to keep in mind about that. Okay, so that was my story about neutrinos, neutrino cosmology. I want to now do a little bit more on this thing that we call model-independent cosmology. So I told you that we all depend on the Bayesian evidence because we need the model, right? And the way people are looking for cracks in the model is to look for data and inconsistencies, right? Because some model-dependent statements are going to be contrasted with some model-independent statements. So the Hubble tension is to say, well, I'm going to measure distances to the C-fates with a ruler, basically. It doesn't depend on the cosmology. And then I'm going to compare that to the inference, model inference from the CMB, in the sense that CMB is a screen, I assume a model, and then I move it forward, right? And then they mismatch. So therefore, the claim is there might be something wrong with the model because if the model was right, they should match. So here we are taking a different approach, and we are saying, okay, what are the elements in the cosmology that we can measure, things that we can actually put a number on, and therefore that don't depend on the cosmological model. So if I'm going to show you a couple of examples, but imagine I was good at doing it, that I didn't make any mistake, right? Then that number should stay there forever. It doesn't depend on the cosmological model. So this is a benchmark that you can use to actually test the other cosmological model. I'm going to give you some examples. One thing I want to emphasize is that so far, all we do is to look on the surface of the pulse light cone, right? Any expansion history, any baryonic acoustic oscillation, any of that is here. But it's much more than the pulse light cone. If I look inside the pulse light cone, which is not casually connected to us, you can also look outside and see what is happening. And once you have all that in place, you can predict the future. That's our dream, right? Well, I mean, if the lambda CDM model was the right one, then I can predict the future. I can tell you exactly what is going to happen. So there are some attempts that we did at doing that, but I'm going to try to start with a very simple approach to model-independent cosmology. So there's that trivial equation that you see there is just basically taking the Freeman-Robertson-Walker metric or any, not only the FRW. If you assume homogeneity and isotropy, then you can write down the A dot, the expansion factor over A is the Hubble parameter, right? So that triviality there tells you that the Hubble parameter is just how time changes as a function of redshift. So I can say, that's very nice, because then what I can do is to try to develop a method to measure the Hubble parameter if I knew how time changes as a function of redshift. Now, this is independent of the cosmological model in the sense that it doesn't depend on the Freeman equation on the energy densities. The only thing I have assumed there is isotropy and homogeneity, and therefore I can test models, right? I can just provide to you H of C, and then you can go and do it. So the big question is, how do I find a clock? Because that's what I need here, right? Well, our attempt was to say the following. There are certain galaxies, certain stellar systems that are very passive and quiet and calm. And therefore, the only thing they have done for a long time is to be sitting there. So if I can actually date those galaxies, I can go and figure out what the delta T is. And I can enter into huge detail here about that, but since it is a very astronomical subject, unless you want me to, I will skip that. Just, we can discuss ad nauseam those things. But what we did was the following. We actually have been doing that for about 10 years, 15 years. And what we can show you here is the Hubble parameter divided by 1 plus Z as a function of redshift. And what you see here is this transition between decelerating and accelerating. So this is the first cosmology model-independent determination of how you go from a decelerating to an accelerating universe. Let me put you the data here so you see what I'm talking about. This is our current data, our current state of the art. These different data points with large error bars is the Hubble parameter now as a function of redshift. But these data points don't depend on any cosmological assumption. So whichever model you have, you can plug it there and see if it fits the data. And as I said, if I have done this correct, maybe not, but if I was able to claim that I did my measurement correctly, then this data will be there for, for millions of years. It doesn't depend on the model, not the model itself. Now, what it is exciting is, of course, these error bars are large, tens of percent, right? But in my defense, there is nothing else there. So these are the only data points. But you can have 0 or 10% or 20%. Now, the exciting thing is that if you forecast what is going to happen with Euclid and Deci, then these are the current data, the black dots. Blue and orange is what should be happening there in about a couple of years. So you can get to that precision very, very quickly. So that's something that one can use and actually exploit and enjoy for that. Now we managed to do it with photometry. And the nice thing of these data sets is actually it's allowing you to figure out where you are in this Hubble tension. So let me say something about that. You take the photometry, you do these neural networks, or artificial intelligence, as they call it today, but you know, fancy fitting. So this is the Planck data as the expansion history goes, and this is the local measurement for the Hubble constant from Riesenthal, right? And if you do this for the photometric redshift, you see that you are sitting here. You prefer to be on the early universe. Now, what is the story that you take from here? Well, the story is the following. These galaxies have seen like a very large range of cosmic expansion, basically from redshift 10 all the way to redshift 0. The CMBs are redshift 1100 screen. The C-fates are redshift 0, or the baryonic acoustic oscillations are between redshift 0 and redshift 1, right? So it means that now you have another probe that is looking at a very, very high redshift length, right? And can actually tell you how the expansion history happens. So it seems like from the CMB all the way down to here, the expansion history is very much lambda CDM. So if you want to solve the tension, you have to touch either the very early universe or the very late universe. And this has been all this excitement about early dark energy and all these kind of models where you put an early dark energy at the very beginning to try to fix this question. The other thing that you can do is to actually go to redshift 0 and change the anchor there and see what is happening. Now, one thing that we did is that, of course, you can now integrate that equation that I showed you at the beginning and then compute the absolute age of the universe today, right? Now, that we have been doing it with globular clusters all our lives. And nobody here is old enough, but maybe you remember there was this so-called age crisis, or now it will be called age tension, right? Nobody believed it. Nobody paid any attention whatsoever. But what was happening is that no matter what people were doing, the ages of the stars were coming out to be much older than the standard cosmological, right? And then, of course, everybody assumed that this must have been wrong because the stars are complicated and all that. At the end of the day, that was not the case. What was the cosmological model? There's another very interesting example that is even maybe more remarkable, which is that now we assume that neutrinos having masses is a normal thing. But of course, in the standard model, there is no mass for the neutrinos. In principle, yes, you can add symmetry terms that are going to give you the mass. But the reason we know about the transparent field is the solar spectrum, right? Because John Bacall said, look, the sun doesn't seem to be giving the right flux of neutrinos, and therefore the neutrinos must be oscillating between eigenstates between the sun and here, right? And everybody told this must be crazy, right? Because how can you tell me that a ball of gas, ionized gas, that it is sitting there is much more precise than my Lagrangian, that it is so beautifully built? Well, it turned out that that was not the case. Neutrinos do have masses, right? So I think it's worth paying attention to these things, you know. You don't have to be religious, but maybe there is some truth about here, right? So what we did with David Balsan, that it is now at Berkeley, is to say, okay, let's do this in the modern way, right? Here's a color magnitude diagram for resolved stellar population for a globular cluster that's for you should be a collection of stars, right? And then depending on how the morphology changes here, then you can figure out the age of the star. That's basically, you're trying to figure out, this is very trivial, it's the proton-proton chain making helium at the core, right? So if you know well the proton-proton chain, then you go to the luminosity of the star and the gravity, and then therefore you know the age. Of course, the complication is that this also depends on the metallicity of the star, of the helium that it had, of the reddening. But what we discovered, and this was the first time it was done, is that actually you can do a full Bayesian analysis on the full morphology of the color magnitude diagram, and you can determine not only that, but the distances, the metallicity, the helium, the dust, and everything. But many papers, and a couple of them more coming in a couple of weeks, but basically this is the bottom line. The universe looks something like this. Now, what does it mean? Well, you can now, let me just talk for 5 more minutes, is that good? Well, the whole thing is coming here, the whole tension idea. So the whole tension idea is the following. You have this baryonic acoustic oscillation service. What they do is the following. They say, okay, there's a sound horizon because you have a plasma that it is cooling down, right? You have your plasma photons and electrons, and there is a point at which these photons, they are being forced into the potential well of the dark matter, right? So they oscillate. But there's a point that the universe cools down, right? So you suddenly get a scale because the photons and the electrons don't talk to each other anymore. So then it's just the last oscillation of this thing. So for every galaxy in the universe, statistically, there is a distance at which there is an overdensity of galaxies. Now, this is statistical. So if anybody is telling you that they saw that in the sky, they are lying to you. Because this should happen for every galaxy around every galaxy and every galaxy around every galaxy, right? So you cannot see it with your eye. That's something else. Because there was a claim about that, and that cannot be right, right? So now, how do you calculate that scale? It's this integral, right? The sound horizon is just the integral between the sound speed of the plasma there over the Hubble parameter at that redshift between redshift 0 and the recombination or the Dirac equality. Now, this equation, everything is model dependent. Everything there is model dependent. You have to assume what the plasma is. You have to assume what the expansion factor is. You have to assume everything. So when they do these baryonic acoustic oscillations, right, here, they do have a model dependence. So you do this plot that you have the early ruler versus the Hubble parameter, then you can start to see what the problem is. This is what is called the tension, the Hubble tension, right? Is that they measure the Hubble parameter at redshift 0 that has nothing to do with the models, and it is this line. Now you do the Hubble parameter from this equation, from the large scale structure and the CMB, and it cuts here, right, at 70. While it should be, this line should be cutting here, right? So that's you should be cutting only at one point, right? But they cut at 2 different points. So which one is the root one? Well, here is where the ages of the universe can give you something and can give you a kind of a hint about what is happening, right? So you can make the same plot as before, but instead of putting the ruler, you put the absolute age of the universe, okay? So ignore this line for a second. The blue one is the resetter. The violet one is the one coming from large scale structure. And this very tiny mark is the CMB, or if you allow for some early dark energy. So you do see that they cut here or here. It's not good. What are the ages telling us? Well, the ages are here, is the blue line, right? And the ages are telling you that they like much better the early universe than they like the local measurement. Now, at that time that I made this plot, these are the 2 sigma and the 1 sigma. Now we have much better data. So the 1 sigma actually became the 2 sigma. So you can think about this like sitting even more here. So from the pure clocking, from the clock's point of view, what I'm seeing is that the expansion history is looking very much like what the lambda CDM model tells me. So I don't know what is going on. Either there are big systematics in the data, and we don't know what is happening here, or maybe there is actual new physics. And what is going on is that we are actually seeing something new that we have to think about. But if it is new physics, it is something very subtle, in the sense that it's not simply changing the expansion history. You have to keep the expansion history the same, lambda CDM, but somehow you change the angles. So I'm not going to talk about something very exciting we did, which is to look at the homogeneity of the universe, which is actually to establish homogeneity from CMB experiments. I'm not going to talk about measuring looking outside the parse-like cone, because I don't have time. I'm not going to look at this, because I had too much material. I was too excited. Not about dark matter either, but I will just put the conclusions and just say the following. Besides some tensions, the lambda CDM seems to be a good phenomenological model to describe the universe. However, don't be too conservative, because otherwise you will miss out on the new developments. So I'm telling this especially to the students, I understand that it's hard these days to do something new and get a job. That's the real problem, right? But when you get a job, do something new, Then is the time for you to try to be. So there are some parsers that remain, but I also want to say something. The field has moved well beyond the spherical counts describing everything to actually do something very precise and accurate. So when you do something, it has to be, you have to provide me with a covariance matrix, you have to provide me with your error estimate, you have to provide me with how the things look like, because otherwise it's going to be impossible to believe. So let me say this, I think it's a tremendously exciting field. More data are coming, it's a data-driven field. Still, we don't know what the dark energy is, what the dark matter is, what the inflaton is, what the early universe is, nothing. So we have to think about how we are going to figure out what those things are, right? Or if it is something else, right? So yeah, I think it's very exciting. So I'll stop here and thank you for the attention. Thank you very much.
More questions for Raul? Maybe I did. I think there was something I missed when you were talking about measuring the age of the globular clusters. So I get that you can measure. You can measure an age for a globular cluster from its HR diagram, but how does that give you the age of the universe? Because the globular cluster could have formed at any time.
So that will give you a lower limit. So formally, that gives you a lower limit.
Yeah, okay.
So now the situation is that you can then see this point as an upper pointing arrow, right? Now, since it is here and not here, the situation doesn't change the conclusion, right? So you can do something better in the paper, which is to actually estimate how much time you have left. So these are the oldest objects that you find around the Milky Way, right? So if you assume the Copernican principle, it should be the same everywhere. And we know now there are galaxies at redshift 12, 11, 12, right? So you say, okay, the only time I have to add is between redshift 12 and infinity, basically. But there is very little time there. So you can assume different expansion histories at different values of the half parameter, and that adds very, very little, right? Of course, you can go crazy and say, okay, well, I'm going to take a different model, right? where I put 100 gigayears there, whatever you want to do. In any case, it's going to make this arrow point up, right? So if it was here, I agree, it was going to be like a more difficult conclusion. But since it is here, it doesn't change the conclusion.
Yeah, because that was what I was thinking. You have to, in some cosmology.
It's a lower,
yeah.
It is a bit of a, you have to be careful because you don't want to use a cosmology to make this inference, right? So this, if I make this plot with an upper arrow, then it's perfectly kosher. There is nothing there that depends on the cosmology. It does depend, of course, on my stellar evolution model. I need atomic physics to tell me how the proton goes into a proton to make helium, right? But besides that, that's all there is.
And in your Bayesian analysis, you have all this stuff to do with like multiple stellar populations and.
Yeah, that's very beautiful. So these are the two papers coming in a couple of weeks with David, which is the following. So we did two things. We allow for arbitrary helium, arbitrary metallicity, element to element, arbitrary screening of the dust, right? And arbitrary ages. And then we say, okay, let's also allow for a couple of populations. You know, maybe there are multiple populations in the cluster. So it's actually very pretty. I don't have the data here, that the ages become very, very robust. So, and the trick to that is to use the full morphology of the color magnitude diagram. So we did something quite nice technically there, is to just do likelihood-free inference, that basically you just look at the morphology of this thing and see how that changes as a function of the input parameter. You use all this BS of machine learning and all that, but at the end, you know, this is just a fitting technique. You know, think about least squares, but better, or splines, but better. Yes.
So that reply was interesting because having read the abstract, I was expecting to hear more about that in the talk than what you actually said, which is fine.
Okay.
I come to be surprised, but you, at the beginning, you made the point about the necessity of using Bayesian methods on the grounds that there's only one universe, which is extremely well taken.
Right.
But another difference between the fields is that in particle physics, when we say the standard model, that's just the name, all right? I mean, if some applied mathematician comes along and starts waving around words like everything's a model, right? I mean, it's just a model, it's just a model, it's just a model. No, I'm sorry, the standard model is not a model. Right? I mean, when we say that we think the group structure is SU2 or SU3, we really mean it, right? We really mean it. We mean that's like a point in conceptual space. Whereas every damned thing in astrophysics is some sort of coarse graining or some sort of model, properly so called, right? That it's an approximation to the reality that's.
You are absolutely correct with that.
So,
yeah, I agree 1,000,000%.
No, and I know you know all this, but I guess the question is, how are we any closer to understanding how strong or weak the dependence of the conclusions is on the necessary coarse graining and use of models and so on?
No, but that's what we should do. So my answer to your question is I fully agree with what you are saying, that we are just having an effective theory here, which is just parameterized by parameters, right? Do we understand what these parameters mean from the fundamental point of view, as it does in particle physics? I would say no. The best example is the inflaton. We don't know what the inflaton is, right? We just have a description, which you draw by hand. It's a scalar potential drawn by hand, right? And then you say, okay, I'm going to try to get closer to that.
But what you just said in response to Kieran's question involving, we relax this assumption and we go to multiple populations,
right.
And we do this and we do that, that felt like a step in that direction.
Right. And that's exactly when I quote this number. I'm very confident about the number, because here is an example where I use the standard model of physics, atomic physics, to actually pin down a number that then you can have to tell me whichever new theory you have about the universe, it has to pass through that number. So if I did it right, that number should stay there forever. Forever. Because I took care of analyzing all the possibilities for that number to be wrong. So, yes, that was the idea, that's the approach that we have in my group, to essentially provide the tools and the means to actually get closer to a fundamental theory of the universe. And I have some ideas that will be another 3 talks on my papers about how to do that. It's a very theoretical part of my life that I haven't presented here, right, about how to do that. But yes, we're getting closer to that, but not yet as close as the particle physicists are. And I agree with you.
Yeah, I mean, the fields are different. That's fine. But
the fields are very different, and the fields move in a very different path, because this is a field that collected data that are significant, to say something, 25 years ago, 20 years ago, right? Particle physics, Thomson and Rutherford, 120 years ago, right? It's a very different pace. I mean, the field is picking up now.
Is there any questions online? Maybe I have again, this is getting to the divide between the cosmology and particle physics, but going back to this issue of the neutrino masses, I mean, I guess in the standard model, you expect that some of the neutrino masses to be the same as related to the same neutrino masses that are measured in an experiment. But is there, I mean, does it have to be the case?
Right? It doesn't have to be the case. Maybe nature is more interesting than that. That's what I was saying, that what we have to do is actually to predict exactly in gory detail what is the signature of those neutrinos as a function of a scale in the power spectrum. Some people have predicted them at higher order correlation, so the 3-point function or even the 4-point function, and then you can call it a neutrino. Because there is not only the mass, you can also look at the sound speed of these things, you can look at the viscosity of these things, you can look at many things, right? So yes, the next step will be to convince anybody that this is a neutrino, is to look at all these different quantities that are attached to a neutrino.
So is there something specifically neutrino-y here, or is it basically just any sort of hot dark matter which is free streaming?
No, I think so. That will be this plot. That is, any hot dark matter is streaming will be like that. But now, if you take into account the viscosity and the sound speed of the neutrino, then no, then it's different. And we wrote a paper about that. Then it is very different, because you want to know it is a neutrino and not just hot dark matter that is streaming, right? This plot, yes.
This is really precision of vector.
This is high precision, but so far, Desi will be close, but not quite close. Look, Desi will be 5% of the whole volume. We have still 95% of the volume sky to play this game. So, for example, since I'm in Australia, when you have SKA working, then you can start to look at much more volumes. I mean, the field still has very few data compared to what I can do.
Any final questions? Let's thank Raul again.
Thanks a lot.